And how we're going to represent that? So how we're going to store the data, right? So we have those nodes, and you have lots of edges. So somehow we want to store them. So there are different ways to store the data using maybe array lists to represent all of the nodes and all of the area of all of the edges. Maybe create objects and so on. But we also have what we call adjacency matrix and also adjacency list. So the adjacency matrix is going to be used for what we call dense graphs. So the dense graphs are the graphs that very basically completely full. We have a lot of number of edges. So number of edges is getting very close. So if you imagine you have n number of nodes, a dense tree is going to have a very close to n number of edges. So basically, that's what we call it. What is it? So we call it a dense graph. Okay, I guess so for a second I muted myself accidentally. So pair graph are basically going to be opposite. So there we don't have, number of edges are a lot less than the number of nodes. So if you have a very dense graph, then definitely matrix is going to be a better option for us to store data, and we're going to see why in a minute in a picture. And adjacency list is going to be much better for a spare graph, as that we don't have too much edges. So let's see how we're going to basically, use any of those representations on which one is going to be better. So this is when we're using the array of vertices, right? So we're showing, a string array of all of the vertices that we have, and then that way it's basically we have to somehow show that edges. So we kind of have the array of edges to show that vertices number 0, which is the index of Seattle, is connected to 1, which is going to be San Francisco, and so on and so forth. So you're going to have an array to show the indexes of each of the nodes, and that is one single of those is going to create one edge. So we're having a array of all of the edges. So that's one way to do that. But then we could also alternatively create an objects of edge, and this is going to be useful especially if you're having the value of weights for each basically edge. So it's a weighted graph, so that's going to make it easier to store the data of weighted graph. So here basically we're going to say node number 1, whatever node is connected to the node number 1, so 0 to 1 connected, and the weight for it, if there's a weight, is for example 2, and then 0 to 3 connected weight for it is 6, and so on and so forth. So that and if there is no weight, you can just leave it at 0 for all of them, and that is going to be a good option as well. But if you're having undirected weighted graph that basically 0 1 0 doesn't matter, they're all similar, there's no specific direction, there's no weight, then this is just wasting memory because objects are expensive. So this is a adjacency matrix. So of course this is for unweighted graph, but you can technically use weight, add weights to this graph as well, or to this table. This is kind of like a table. So it's a two-dimensional table. Every line of this two-dimensional table every row is going to be one of our cities, and also columns are going to be exactly same cities, right? So basically row and columns are going to be cities, starting from Seattle all the way to Houston. And we have a table on the top, same thing. So the first column is Seattle, connected to Seattle. So Seattle to Seattle, there's no edge, so it's 0. But then Seattle, so that's when I'm going to second column, which is San Francisco. San Francisco to Seattle, there is a connection. So we can go back to the diagram just to clarify that. San Francisco to Seattle, there is a connection, right? So that's the edge. So that is going to be shown here on the matrix. So basically on the matrix, if there is an edge between two states, you're going to put 1. If there's no edge, you're going to put it 0, and so on and so forth. So that's how we're going to have created this table. But the problem has, just if you're looking, I'm kind of showing it in this table, if you're looking in the half of this tree, everything on the top half is exactly repeated in the second half of this tree as well. I'm trying to see, well, I see that the monitor is not showing things well. Okay. I guess to fix the problem. So now hopefully you can see this picture better. So this, if you think about half of this array, anything that they have to on top of this red line, it's going to be exactly repeated of what we have in the bottom of it, because it's an undirected, unweighted graph. So everything, from 0 to 1, whatever happening, same thing is from 1 to 0, right? So that's exactly going to be repeated. So we have a duplication of data that we store. And imagine if you have n nodes, how much extra information, how much extra space we use. So this is basically because this graph is a sphere graph, and it's not directed. So we have an extra information, and we also have a lot of zeros if you look at it, because again, this is a sphere, and this doesn't really have too much of a number of edges. So this is wasting of a space. This is better to be used, or the better way to store this data is using the adjacency vertex. So this is adjacency vertex list. So again, we're going to have an array that it's kind of arrays of arrays again, and we're going to store the neighbor, all the neighbors, all the states, and then we're just adding who are the neighbors. And the neighbors are connected through exactly one edge, so we know that they're connected to each other directly. So that means there is an edge between them. So the neighbors to Seattle is going to be San Francisco, number 3, Denver, and number 5, that's going to be Chicago. So those are the only neighbors for the Seattle, for example. And then we do the same thing for San Francisco, and so on and so forth. So that way, as you can see, we're storing a lot less data, and it's a lot easier and faster to search for the information. But if you have a very, very dense graph, and so Seattle was like almost neighbor by every single other state, and the same thing was for every other one of those, so we had a huge number of edges, you could imagine that each line would be potentially go all the way to n. So that would really creating a huge number of information and huge table. So in that case, definitely adjacency matrix would be a better. This is same thing, adjacency list, but also, and instead of just putting the index for each neighbor, we're using the entire edge as an object. So that would be another way to do that. It's a little bit more memory, but it's good if, especially if you have a particular information you want to add, like a weight. So definitely you cannot add any weight in this list unless you're using the edge as an object. So if you have extra information you want to add, you want to need to use a list, but then add an object into it. If you want to use matrix, you can still add the weight, because whatever you have there as 1, it can be changed to the weight of it maybe, right? So that would be like one way to do that. Or you can also use the matrix of edges as an object. That's the difference between adjacency list and adjacency matrix. And now we know where we have to use each of them, right? So if you have a huge number of edges, then you're better off by using a table like matrix. If not, then just list is enough. When we're storing this data, that after we store, we were able to retrieve them, we should be able to traverse them as well, right? So that's going to give us a lot of information, like there are lots of algorithms for us to traversing the graph and get us a lot of information that is necessary to solving a lot of different problems, right? So when we're traversing the graph, we're using those very famous algorithms that we use in the tree, DFS and BFS algorithms for for traversing the tree, and we're going to use the same thing to traversing our graphs. And when we do that, the result of both are going to give us the different kind of spanning tree, which is going to help to solve different kind of problems. So we're going to go over the algorithms real quick again. We already know the algorithm for DFS and BFS. It's going to use the same algorithm. We're going to just basically just review them, and then we're going to go over one example just to see if we understand the algorithm correctly. So DFS is depth first, right? So we're basically going to one branch, we go over that, going to one child, we go over all the children of that child first, and then we go backtrack. So in the tree, we know it started from a root. So the graph doesn't have any roots. So we just have to pick one of the nodes. And usually we're just starting from the node that is stored in the index 0. If you have an array or matrix, whatever we have, the very first set we have is index 0. We usually start with that, right? Because again, we don't have any particular roots. And then we don't have any left child or right child, right? So we're just going to start from the very first child, whatever child we have, and then we go to the child of that child and the child of that child, unless we get to the point that children doesn't have any more children, then we start going back track and find the other children. So this is exactly what the algorithm is also telling us to do. We find one of those, just one of the sorry, I have this allergy that's not getting any better in this weather. So we are starting with one of the nodes as a root. We imagine it's root, and we start visiting that. And in order to visit that, we keep going to go to all of their neighbors of that. So we keep going to the neighbor, we visit that neighbor, and we go to next neighbor, visit that. And we want to make sure that each node only going to have one parent and only one parent. And we're going to do this in a recursive manner for each, basically, for each of those W nodes that we find. So let's apply that to this graph. So the graph at index A. This was the entire algorithm. I guess you may not see the whole thing. So this is going to be the example that we're going to use. We're going to use a DFS to solve this one. So our graph is going to look like this, right? So index 0 is the first one. We're going to start with the index 0. And again, we're going to over the indexes, right? So from 0, we're finding the very first child, and we're going with a lower index. So we're finding 1. And so this is going to be like a recursive algorithm. So from 1, we're going to go to one of the children. Again, we're going to go with the children with the lower index. So we go to 2. And then from 2, we're going to go to one of the children. So again, we're going to go with the children with lower index that we haven't visited it yet. So 0, we already visited, right? So we have to go to 3. So we're going to see 3. And now we're going to go to the children with the lower index of 3 that doesn't have any, we haven't visited. So the 3 only have the 0 as its own children and doesn't have any child, right? So, and we already visit 0. So we have to backtrack. So we have to stop. So we go back to 2. 2 doesn't have any children that we haven't visited yet. So we go back to 1. And now 1 has 1 extra children or child that we haven't seen yet, and so that's 4. So if we draw this graph, as you can see from the blue line, the tree is going to be look like this. So we have 0 on the first, and then we have 1, and then we have 2 and 3, and then over 1 we have another one. So basically the tree is going to be look like this. Let's try to draw this tree on this whiteboard if I can.